Laurence Geffert is going to come and talk about 32 years of ocean data to faster offshore wind farm consent. Wow, that's a really politically touchy one. I'm really excited about this one, I have to say, because the wind farm consent is something that we see all across the planet being contested. I don't know if that's the kind of wind farm consent that we're talking about, but if not only my compatriot in the United States would stop criticizing wind farms for absolutely no reason, that would be great. Now, back to the topic, OceanOS CTO Laurence Geffert. Please welcome him to the stage. Thank you very much for your presentation and for being here. Thank you.
Thank you very much.
Thank you.
Hi, it's great to be here. I'm so excited to be in this room where so much brilliant science is being shared and presented. And it's really something that we couldn't run our company and do the things that we do without. So I want to start off by thanking all of you for all your work. We really appreciate it. My name is Laurence Geffert, Dutch spelling, German pronunciation, but it's okay. I am here for OceanOS, and we are a very small, early stage startup in the UK working on offshore wind farm consenting. Now, I think somebody said earlier, science always starts with a question. I am here to present the commercial lens. We always like to start with a problem. And in the startup space, they say, don't sell a vitamin, sell a painkiller. So let's start with the problem and the pain. And that is that currently environmental uncertainty adds years and millions in delays to every offshore wind farm project. So it takes about 4 to 7 years to get the entire project, a new development signed off. It costs between £2 and £5 million and takes surveys, back and forth between the regulator, the developer, local communities, NGOs. However, there's no single platform to do this. There's a very fragmented ecosystem where data is just being pulled into different systems and kind of pushed around. And most importantly, I think, most of the data that we have that informs the planning is based on the past, but not on the future. And this is, of course, highly, highly relevant, especially given the geopolitical situation where we're worried about national energy sovereignty, energy prices, but at the same time, we don't want to forget about local communities and ecological impacts as well, right? So any kind of speeding up of the process really needs to take those into account as well. But in the UK, for example, there is this target, a political target, of reaching 50 gigawatts of offshore wind by 2030. Right now, we're at 15. 4 to 7 years to sign off these projects. We already know we're not going to make that target, so something needs to happen. So what we have developed at OceanOS is a marine geospatial foundation model that we think can help with speeding up this entire process. Who here in the room is familiar with the geospatial foundation models, the whole idea, the concept, vaguely? 2 shy hands here in the front, some back there, but I would say overall maybe 10–15% of the audience. Okay, so I'll explain this a little bit. A geospatial foundation model is essentially the marine equivalent of a large language model. So think what ChatGPT does for human language and text. The geospatial foundation model is supposed to do for geospatial temporal data from Earth observation and other geospatial data sets. There are increasing numbers of geospatial foundation models around for the terrestrial realm, Prithvi, Aurora, and so on and so forth. But to our knowledge, there isn't an example from the marine realm as of yet, and this is what we're trying to change. This is purpose-built on 32 years of multi-model ocean data. Right now, we're using Copernicus marine data, which has been pivotal in getting this together and off the ground. And this foundation model, the advantage is it can provide higher accuracy and scale than traditional ML models, even with small amounts of training data, which, as we know, is a huge issue in the ocean. Here is a more technical overview. Sorry, the colors are not exactly what I imagined they would be. But we start on the very left with these environmental layer inputs. So as I said, this is Copernicus reanalysis data right now at level 4. But we really want to move up the value chain and go to level 3 and level 2 data sets as well, which is work in progress. It's not trivial, so it's going to take us some more time. These environmental layers, basically, a spatiotemporal Zar cube, goes into the model and is masked. So we mask out 75% of the pixels. We started off just randomly masking them out, but then found that spatial autocorrelation was basically the largest signal that the model would pick up on. And so we started employing custom masking strategies such as temporal slicing, where we block out an entire month, for example, and spatial masking as well, where we would block out a whole chunk in the middle of a chip, for example. This is put through something called a patchify operation, which groups together pixels and give them a shared latent embedding, which is needed to keep the computational volume to a manageable level. And then we add some additional metadata. You can see these 3 slices here. So we have a positional encoding that basically just tells the model where all the pixels are in relation to one another. But then we also add information about where in the world this pixel is so that the model can learn things about latitudinal gradients, for example. And we add other metadata as well, such as time, so it can learn about seasonality and scale, so that eventually we'll be able to put in different kinds of observational data sets and the model kind of understanding what scale of phenomenon it is currently operating on. And then finally, it says here static, which is right now bathymetry, very importantly, because of course bathymetry informs a lot of the ocean processes, but we didn't want to input bathymetry into the model, because in earlier iterations what we found was that the model would just memorize it and then cheat by looking up the bathymetry map and inferring the variables that way. All of this is put through an encoder and creates a latent embedding, 256 continuous values that kind of encapsulates a dense representation of the input information. We decode it again and reconstruct the inputs, including the masked pixels. And that is the training task that the model learns on. And then we can evaluate the performance by just looking how well it does on the reconstruction. Now, this pre-training is supposed to teach the model something about ocean dynamics and how the variables relate to one another and what an ocean eddy usually looks like, for example. And then in inference, oh, sorry, I have a visualization here. So this is hot off the press. I think Jan LeCun once said, if you want to visualize 256 dimensions, you say 256 dimensions 256 times, and then you visualize it in 3 dimensions. So that's what I've done here. This is a PCA, top 3 principal components, and then just over 1 year, the signal of what the model sees. And I think it's quite interesting. You see here, for example, the Mediterranean, relatively stable, dominated by these green colors, and a lot more change going on in the Atlantic, which is, of course, a more dynamic environment. You can see signals like a latitudinal gradient. You can see coastal versus open ocean, and then just everything blending over the course of the season. Yeah, but we didn't create this model just to make a colorful map, though I love colorful maps. We want to use it to act as a platform that we can host other downstream applications on top of. And offshore wind farm is, of course, one, because it can give us a baseline and a kind of more holistic understanding of the environment that the wind farms operate in. And so this is what we want to use with a kind of agentic RAG interface to allow regulators to understand the environment they're operating in much, much faster. We are also exploring using this in species distribution modeling and seasonal anomaly detection for example, marine heat waves. harmful algal blooms, and coral bleaching as well. Eventually, this will end up informing a platform that should look something like this, a web map interface, where then you can upload your polygon with maybe some turbine placements. And it'll then automatically highlight certain risks for you, environmental risks like marine mammals, seasonal bird migrations, and other ecological factors like that. This is the team working on this. So as you can see, there's not that many of us. We're pretty early stage and small, but we're trying to scale this up. And with that, I'm at the end of my time. Thank you very much for your attention.
Thank you very much, Lorenz. Is this, in your opinion, going to be integrated into decision-making processes with some inequality or with cultural differences? Because what you mentioned about the difficulty for offshore wind farming in the UK exists in France, exists in the United States. We're talking about, I would almost say, a global phenomenon. Have you kind of anticipated that? Yeah.
Yes, that's a very good question. So the model is global, and I think we could use it in many, many different legislators, contexts. However, we are focusing on the UK right now because we have existing relationships with the regulators like CFAS and DEFRA in the UK, who are in charge of this process, are aware of the political problem that I mentioned earlier with the 2030 target, and therefore are, I think, quite willing to give us regulatory sign-off, which is the most important thing for us in the offshore wind farm use case.
And do you adapt the methodology, the technology to understand? I mean, is that relevant to kind of cross it with, or to?
Yeah, I think more important would be to have somebody who knows the local or national market and regulation and processes, and like you say, also cultural contexts, right? So if we were to transfer this to another country, we would probably need an expert who helps us localize all of this.
Great. Fantastic. Another good example of application of how AI is changing the way we're doing modeling, and for very, very concrete uses. Thank you very much, Lorenz. Let's welcome you back to the floor.
Thank you very much.
Thank you.